Swayam Prabha. Digital India. Educated India.
In the last classes, we had discussed about solids and liquid rocket engines. Let's firstly summarize what are the various features of solids and how do they compare with liquids before we move on to hybrid rocket engines. So if we take one of the key features that is different between a solid rocket and a liquid rocket is that if you look at the performance, that is ISP of solid rockets varies between something like 2200 to 2600, right? This is at sea level. What about liquids? That is for liquid oxygen, liquid hydrogen. But if you are looking at earth storable, it starts somewhere at around 2800 to something like 4400. One of the reasons why this happens is, as I had said earlier, that if you look at solid rockets, you need to have the fuel and oxidizer in close proximity, and that is a serious constraint in the choice of what you can use as fuel and what you can use as oxidizer. But whereas in a liquid rocket, you store them in separate chambers and only inject them into the combustion chamber when required. So that gives you the freedom to choose good liquid and a good fuel and a good oxidizer, which is why you will find that specific impulse of liquid rocket engines are much higher. Now, if you noticed, the liquid rocket engine as such was a very complicated design. It had a lot of valves, moving parts, right? If you are using a pump fed system, then it has turbo pumps, turbines, everything there. So the design is not very simple. And we also said that it requires a lot of manufacturing capabilities to make a liquid rocket motor, because you need to have various manufacturing abilities like drilling very small holes and then removing the burrs and other things, which is sometimes not very easy. So whereas if you look at a solid rocket motor, all that you have is, once you load the fuel and oxidizer, the design looks very, very simple, right? So The other advantage in a sense of a solid rocket over a liquid rocket engine is the following, that if you look at a solid rocket engine or a solid rocket motor, we discussed about this, that the density impulse is quite high, right, because primarily you are using high density solids to make up this, and therefore the density of this will be density of the propellants themselves will be very high, and consequently the density specific impulse will be higher. What it would indicate is also that if the density specific impulse is higher, then the volume is much smaller, right. Now, if you look at a liquid rocket engine, and especially if you look at liquid hydrogen, liquid oxygen systems, for example the space shuttle, if you look at the space shuttle, the tank that is there on the back side of the orbiter, that entire tank, a large part of the volume of that tank is occupied by the liquid hydrogen tank, simply because the liquid hydrogen density is very low, and it's of the it's around 70 kg per meter cube. So you would require a very large volume for this. So as a consequence, its density impulse is lower. What does large volume, how does large volume contribute to a bad thing? If you look at if its operation in the atmosphere, then the drag will be very high, right. Then if you look at solid rockets have what is known as shelf life. That is, you can make them and store them for a few years, typically of the order of 10 to 15 years. Okay, and because of this feature, it is used predominantly in the defense industry, simply because you will not know when you would require to use it, and therefore it is better to make them and keep them so that you can use as and when required. Whereas if you look at a liquid rocket motor, a liquid rocket engine, although the specific impulse is much higher, you will still have to, it does have some kind of shelf life, but you cannot store them for such long time. So typically what you will do is you will load this propellants as and when needed, right. So it has as a consequence, it has very limited shelf life. And therefore you will find liquid rockets hardly used in defense industry, whereas it is predominantly used in the launch vehicle industry. Okay. Now if you look at liquid rocket engines, we said that this is simple to design and construct and all that. There is a flip side to this. The flip side is, if it is very simple, then your controllability will also be very poor, alright. If everything is simple, then that is the price that you pay for it. So, as a consequence, you will find that the solid rockets have very little controllability. That is, once you start it, it's in some sense very difficult to switch it off. Okay. So the start, stop, restart feature is not there in a solid rocket motor. Whereas if you look at a liquid rocket motor, because the liquids are either fed into the combustion chamber through a pressure fed system or a turbo pump fed system, you have the ability to control their flow rates or stop their flow, and therefore you can have start, stop and restart with liquid rocket engines. Now, in addition to this, changes in the thrust level, that is throttling of the thrust, is not possible in solid rockets. It is certain through a design itself, that is online you cannot change its thrust. There is a set design and it will follow that particular set design. Whereas in liquids you can throttle the thrust by altering the flow rate of the fuel and oxidizer. The other thing about solid rockets is because you have them stored in the same chamber, right, there is a risk of either a fire or an explosion anytime during manufacturing or storage, transportation, or even during operation. Okay. The chances of it going wrong is very high. So therefore it is not such a safe system, right. such a risk is not there when you look at a liquid rocket engine, simply because the fuel and oxidizer are stored in separate chambers, right. They are only introduced into the combustion chamber during operation. So in addition to this, if you look at the solid rocket motor, we discussed this in detail, that its burning rate is a strong function of pressure, right. So the burn rate is dependent on pressure, and therefore any fluctuations in pressure kind of feeds back and is very disastrous, can have very disastrous consequences. Now if you look at liquid rocket engines, we discussed this that even the engine portion needs cooling, right. Whereas in a solid it is automatically taken care if the configuration is a port burning configuration, because the propellant itself prevents the heat from reaching the walls of the combustion chamber. So whereas if you look at solid rocket motors, as I had said earlier, because of the way in which it is designed, the propellant itself acts as a inhibitor or an insulator, sorry, in this case, right. It does not allow the heat to be transferred to the walls of the combustion chamber. Now these are some of the advantages and disadvantages of or comparison of solid rockets versus liquid rockets. So these came in first, and then people thought, looking at it, is it possible to have a hybrid of these two systems, and which is what is essentially a hybrid rocket system, okay. So here typically you can have either a solid fuel or a liquid fuel, or a solid oxide or a liquid oxidizer. But what is typically used is a liquid oxidizer and a solid fuel. Simply because if you look at all the oxidizers that are known to us, they are crystalline solids. So it is very difficult to make a propellant grain with very good mechanical properties with these solid oxidizers, solid oxidizers. So therefore in any hybrid rocket system you will find that the fuel is solid whereas oxidizer is liquid. This can also be in some cases gas, so liquid or solid, liquid or gaseous oxidizer. Now if you look at a typical hybrid rocket system, it is as shown in this figure here. As I said, it is a combination of both a solid rocket as well as a liquid rocket, and the fuel here is solid, and the port of this fuel acts as the combustion chamber, right, and the liquid is stored separately and is either fed through a pressure fed system or a turbo pump fed system depending on the thrust level and the time of operation. So in a sense this combines the features of both solid rockets and liquid rockets. In some cases you need to have an igniter system here so as to ignite the combination, and then the combustion will take place. There are designs which are hypergolic, that is if you use N2O4 and certain compositions of solid fuel, you can have a hypergolic combination. So the design of this, if you look at now what are the advantages of this hybrid system, right? If you look at this design looks fairly simple, right? Because if you look at it, you are only handling one liquid line, right, whereas in a typical liquid rocket engine you had two liquid lines, and that has been substituted with one liquid line here. So the complexity has been reduced by half. So let us look at what are the other advantages of the hybrid systems. So in a sense if you look at it, its complexity of design is in between that of a hybrid solid and a liquid. It is design is less liquid rocket engine, because you are dealing with only one fluid. So the number of valves, pressure regulators and other things are reduced by half. So in that sense the design is less complicated when you look at it as compared to a liquid rocket motor. But the biggest advantage of a solid rocket as compared to hybrid rockets as compared to solid rockets is its safety. If you look at why this happens, okay, we are saying safety even during fabrication, storage and operation. If you look at how the mass flow rate is generated in solids, liquids and hybrids. If you look at solids, firstly the mass flow rate m dot, it is given by rho p ab APC to the power of n. Okay. So it is sensitive to the pressure, as I had already said, and we had discussed this, that if n is high, the chances of explosion are much larger because the pressure gets amplified due to, if there are changes to the burning surface area or other parameters, then the pressure gets amplified because PC goes as 1 by 1 minus n. So therefore if you look at solids, this is how the mass is generated, and if you look at liquids, the m dot is given as CD A injector this is mass of injector, so mass of fuel, so I will put this as, and similarly you will have oxidizer also, the N here indicates the number of injectors, NF and NOx. Okay. So this is how the mass is generated. Now if you look at what happens in a hybrid, as I said earlier, it is a mixture of these two. So the oxidizer mass flow rate follows a similar thing, whereas fuel will follow something similar to this. But as I said, the safety comes in because of something known as boundary layer combustion, right. If you look at the oxidizer is injected like this in the port, right. The fuel is here, and once you ignite it, the oxidizer gets vaporized, okay, and there is a boundary layer that is formed. Fine, the boundary layer is indicated by this black line here. Now, once the boundary layer forms, then what happens is the oxidizer diffuses in and the fuel comes out. They mix and combust along this red line. So, the combustion is essentially diffusion dominated, right. What is it that we have learnt about diffusion combustion? We had said earlier that if the combustion is purely diffusion dominated, then the pressure index is 0, right. So, it is independent of pressure, and that is a very big advantage in terms of hybrid rocket safety. And now, if you look at how the mass is generated in a hybrid rocket, it is the fuel mass that I am talking about. Oxidizer is according to the relationship that we already have, but if you look at the fuel mass, it is still rho p a b r dot, but the burn rate here is given as where GOX is nothing but mass flow rate of mass flux of oxidizer. So, if you have a hybrid rocket motor like this, with this being dP or the port diameter and m dot OX being the oxidizer flow rate, the burn rate is a function of the mass flux of the oxidizer. Okay. This is something similar to what we discussed earlier in terms of erosive burning of solid rockets. If you remember, there also we said as you go from the head end to the nozzle end, the Reynolds number keeps increasing, the boundary layer thins, and therefore you could have erosive burning. The phenomena is very similar here too, right. It is a strong function of the thickness of the boundary layer, and the boundary layer is dependent on the mass flux. So, that is why we have such a relationship. So, the overall mass burn rate m dot fuel in this case would be now A is nothing but, just as in solid rockets we had A there, which we said is the burn rate at unit pressure. This is also the burn rate at unit mass flux. Okay. So, what is typically done is we plot R dot versus GOX on a log scale. Therefore, if you on a log scale, if you get a straight line, then the slope of that straight line will give you n. Okay, that is what you will get here. This is very similar to what we had in solid rockets. So safety is one feature, then the reduction in complexity is the other. Then if you look at it, you can have start, stop, restart like a liquid rocket, simply because you have one liquid, right? If you let the liquid flow, you can start, and then if you stop it, you can stop the motor. So then throttling is also possible in this case, simply because you can vary the flow rate of the liquid, and therefore you can get variation in thrust. Something like a variation from 8:1 is possible. Okay. If you look at the specific impulse of these systems, in some, this is something similar to what you have in liquids, right? You can store fuel and oxidizer separately. So therefore, you will find that it is possible to get a higher specific impulse compared to a solid rocket, but the specific impulse is lower than a liquid rocket. Okay. Then again, the density impulse is something in between solids and liquids, because you are using the fuel as solid here. Okay, so and if you look at this in comparison to a liquid, in a liquid we said you need active cooling of the combustion chamber. Here, because you have a fuel block, that acts as an insulation between the combustion chamber and the motor casing, so you do not need any kind of active cooling. So the major advantage in this case, in addition to safety, is the cost. Okay. If you look at solid rockets, because you need to have a certain set of mechanical properties and also you need to have them in close proximity, you have to in some sense engineer fuels or binders. The hydroxy terminated polybutadiene is one such chemical. Okay. So you cannot use any kind of polymer, and therefore if you look at it, the cost of having a solid rocket motor would be very high. And also if you look at solid rocket motors, you need to have very elaborate procedure to check for cracks and other things, because if the propellant has cracks, then it is a very serious problem in solid rockets. So you have to kind of cast them in segments so that even if one segment goes bad, you can replace it, which again adds to costs. And then you have to have, after you have done everything, you have to have a non-destructive evaluation of the entire rocket motor, which is again going to be expensive. In the case of hybrids, even if you have cracks, it is not going to be detrimental, simply because the burning rate does not depend on pressure, whereas in a solid it used to depend on pressure, and pressure used to be very sensitive to changes in burning surface area. So that kind of coupling is not there in hybrids, and therefore it is very safe, and in addition it is very much cheaper compared to both liquids and solids. In the case of liquids, if you look at it, the regenerative cooling, right, and the kind of care that one needed to have in designing the injectors, all that is taken away to a great extent here. You are only injecting one liquid, so you do not need to impinge one on the other, right, and all those problems are taken away. So the manifolding is a lot more simpler because you are only dealing with one liquid. So in that sense, the cost of this is much lower than either solids or liquids. One of the other things is that if you look at it, you are looking at a fuel. Any kind of polymeric material is good enough to be a fuel. Okay, so that is the reason why you can kind of choose any kind of polymer, rubber, right, polyethylene, all these things you can use, and therefore the cost of it is very much less. If you look at Soyuz rocket motor, right, Soyuz has the distinction of being this launch vehicle that has had many flights, more than 1,000 flights. Okay, and the reason that it is chosen as one of the vehicles to transport people from Earth to the space station is because it uses predominantly a liquid oxygen and liquid kerosene system. Okay, if you look at a liquid kerosene system, liquid oxygen liquid kerosene system, the cost of it is much cheaper than any other system, and that is one of the other advantages with Soyuz. So therefore it is been used very frequently for transportation of men and material to space station. That is a liquid engine, and I said the hybrids have a even further advantage because if you look at any kind of polymer and kerosene, the costs are very similar, right. The kerosene used there is not something that is available, it is an aviation grade kerosene, because you have to take out sulfur there, right. The sulfur content has to be reduced very much, otherwise it can be a very corrosive thing. So the cost of hybrids can be even lower than what you have in liquid rocket engines. Okay. So that is these are the advantages of liquids. I have been kind of telling you things that make you think that, you know, hybrids have such a phenomenal advantage over solids and liquids. Now if you turn back and ask, has it ever been used for either in a launch vehicle or a missile, the answer is no. Okay. Now you might be wondering, why are you know, past engineers so dumb they don't see these kind of advantages that we are seeing. But the fact is, there are a lot of disadvantages with hybrid systems, which we are going to discuss in the next class, which make it something like not usable currently, right. If you look at hybrids, the only kind of application that it has had till date is that it has been used on Spaceship One, right. Do you know what a Spaceship One? The one this was the X Ansari prize. There was an X Ansari prize that was there for taking man to suborbital flight and bringing them back and repeating the mission within 15 days. Okay. So anybody who does that would have got the prize. The designer who got this was somebody known as Bert Rutan, and the vehicle was Spaceship One. They used a gas turbine engine to take it to a certain altitude and Mach number, something like 0.8 Mach number, beyond which this system that went to suborbital flight was dropped, and then it worked as a hybrid rocket motor and then went up. Okay, stayed there and then came back. Now if you look at it, it is strictly speaking not a perfect mission. If you look at launch vehicles and missiles, at the end of the thrusting phase, you need to have a particular velocity increment and a particular altitude achieved, and the kind of tolerances that are there are very, very small. In this case, there was no such thing. You just had to go to a suborbital flight and come back. Even if it went 5 kilometers higher or 4 kilometers higher, it didn't matter. And even if it had not the required velocity, it didn't matter either. So if you look at it, it has not been strictly used in any kind of mission. So in the next class we will discuss it, what are the disadvantages this has, which is preventing it from being used in any application. Thank you.